Hi students, in this session I am going to explain you the topic convolution. Okay, so what is convolution? I will give you the introduction about the convolution, and I will explain the concept of convolution in time domain and frequency domain along with the properties of a convolution. So we will discuss these topics in this class. First I will start with the introduction. Okay, so what we know about convolution? Simple. Convolution is a mathematical operation or mathematical way of combining two signals to form a third signal. Here the convolution is nothing but it is a mathematical operation which combines two signals and it generates a third signal or new signal. Simple. We will perform the operations like addition, subtraction. There two signals will be added and it will generate a new third signal. In the same way, convolution is also a mathematical way of combining two signals to form a third signal like addition, subtraction, multiplication. Convolution is also a mathematical operation which will combine two signals and forms a third signal, that is a new signal. Okay, you combine two signals to form a third signal. Here the convolution relates the input signal and the impulse response of the system to the output of the system. Here the convolution relates the input signal and impulse response of the system. Here mainly the convolution relates input signal generally represented with the x of t. Okay, and impulse response of the system is generated with h of t, generally represented with h of t. Now it relates x of t and h of t to the output of the system y of t. So here generally we take the output of the system as y of t. So convolution relates these three, that is input signal and the impulse response of the system to the output of the system. Here the system is LTI system, linear time invariant system. Generally we consider this convolution for LTI systems, linear time invariant systems. Okay, simple. Convolution is a mathematical operation of combining two signals to form a third signal as a new signal. Okay, simply here the two signals which will combine is the input signal and the impulse response of the system. So here we have considered the input signal x of t and the impulse response of the system h of t. We have to combine these two signals and to form a new signal, that is the output of the signal y of t. So it relates input signal, impulse response and output of an LTI system. Okay, this is the introduction about convolution. Now we will go on to the concept of convolution. I will go for the concept of convolution. So I will explain. This is for LTI system, that is linear time invariant system. So I am considering an LTI system, linear time invariant system, which is relaxed initially at t equal to 0. Which is initially relaxed at t equal to 0. I consider an LTI system which is initially relaxed at t equal to 0. Now we all know that any arbitrary signal x of t can be represented as. So we all know that any arbitrary signal x of t can be represented as x of t equal to integral minus infinity to infinity x of tau del of t minus tau d tau, del of t minus tau d tau. So here see, here del of t minus tau d tau is nothing but the delayed impulse input. So impulse response of the system is nothing but the output of a system for an unit impulse as input. That means for this system, if we give the impulse as input, unit impulse as input, then the output produced by the system is nothing but the impulse response. Okay, now here this del of t minus tau is the delayed version of this del of t, that is this unit impulse signal is delayed by tau seconds. Here any arbitrary signal x of t can be represented as x of t equal to integral minus infinity to infinity x of tau del of t minus tau d tau. This is a general expression. Now from this expression I will get the relation between input signal, impulse, response of the system. So we'll get the relation of x of t and h of t. How it is related to the output of a system. So I will get all this from this equation. Now, see, if the input is an impulse, del of t, then the output is denoted by h of t. I already explained. If the input for a system is an unit impulse del of t, then the output or the response produced by the system is nothing but the impulse response, and that is denoted by h of t, called impulse response. If input is an impulse del of t, if input of a system is an impulse del of t, then output of the system is denoted by h of t, simply called as impulse response of the system. So consider a system. For this, the input is impulse del of t. So the output produced by system is nothing but impulse response, which is nothing but h of t. Now h of t can be written as h of t transformed version of del of t. H of t can be written as transformed version of del of t. Why? Because we all know if x of t is the input which is given to a system and it is producing an output y of t, then y of t can be written as transformed version of x of t. In the same way, h of t is nothing but a transformed version of del of t. Okay. Now see the system output. Now the system output is given by y of t equal to transformed version of x of t. So there is a system with input x of t and output y of t. Then the system output y of t is given by y of t equal to transformed version of x of t. Already I know the equation of x of t, that is integral minus infinity x of tau del of t minus tau d tau. So that I can write this as transformed version of integral minus infinity plus infinity x of tau del of t minus tau d tau, because I substitute the value of x of t in this equation. Okay. Now I consider this as a linear time invariant system. So we know that for a linear system, we can write this equation as y of t. Y of t will be equal to, see, integral minus into infinity x of tau, and I am bringing this transformed version to the impulse. So I am bringing this. So this is for a linear system. Okay, I consider this system as a linear time invariant system. So for a linear system, y of t will be equal to integral minus infinity x of tau, a transformed version of this one, transformed version of del of t minus tau d tau, Simply as a linear system, I can bring this transformed version inside of this integral. Okay. Now the response of the system due to the delayed impulse. See, I am considering response, nothing but output of the system due to the delayed impulse as h of t comma tau, delayed impulse. See, delayed impulse is nothing but this one, delayed impulse. Actually, impulse is this one. If it is delayed by tau seconds, then how can I write del of t minus tau? That is the impulse, unit impulse is delayed by tau seconds. Now see, response of the system, nothing but response is nothing but output of the system due to the delayed impulse. If the impulse is delayed by tau seconds and it is given to a system, so here there is a system. For this I am giving the input as delayed impulse del of t minus tau. Now for this type of system, the output it will generate is denoted as h of t comma tau. I am considering this as h of t comma tau. Where this h of t comma tau is the output of a system for which the input is delayed impulse. So the response of the system due to the delayed impulse is taken as h of t comma tau. Okay. Now write it as an equation form. h of t comma tau is nothing but the transformed version of del of t minus tau. So h of t comma tau is nothing but the transformed version of del of t minus tau. So I got an equation for h of t comma tau as transformed version of del of t minus tau. Now the system output y of t will be equal to integral minus infinity x of tau. In place of this I can write h of t comma tau. So finally I got y of t equal to integral minus infinity x of tau. In place of this, already I know this, the transformed version of del of t minus tau will be equal to h of t comma tau. So I write it this h of t comma tau d tau. Finally here I got y of t equal to integral minus infinity x of tau h of t comma tau d tau. Okay, so I consider linear time invariant system. So we all know that for a time invariant system, output due to the delayed input is same as the delayed output. For a time invariant system, we all know that output due to the delayed input is same as the delayed output. So I am applying that concept here. See, here h of t comma tau is the output due to the delayed impulse, because impulse is the input of the system. For that I am considering the impulse as the input of the system. So h of t comma tau is the output due to the output response due to the delayed impulse, that will be equal to the delayed output. In generally, if the input is del of t, then the output is h of t. Okay, so the impulse is delayed by tau seconds, written as del of t minus tau, and the output produced by the system I am considered as h of t comma tau. Now the output due to the delayed impulse is same as the delayed output. For impulse, the output is h of t. So delayed output is h of t minus tau. That is, as the input is delayed by tau seconds, the output will also be delayed by say tau seconds. Here the impulse is delayed by tau seconds. So the output h of t will also be delayed by tau seconds. So for a time invariant system, we can write the output due to the delayed impulse, that is h of t comma tau, will be equal to delayed output, that is the output h of t is also delayed by tau seconds, that can be written as h of t minus tau. So h of t comma tau will be equal to h of t minus tau. Simple one. So for linear or for time invariant system, we can write output due to the delayed impulse is same as the delayed output. So in place of h of t comma tau, I can write h of t minus tau. So in this equation, the y of t converts to y of t, changes to y of t equal to integral minus infinity x of tau. In place of this, I can write h of t minus tau d tau. So finally I got the equation of y of t as y of t equal to integral minus infinity x of tau h of t minus tau d tau. Y of t equal to integral minus infinity x of tau h of t minus tau d tau. This is called convolution integral. This is called convolution integral, or simply convolution. We call it simply as convolution. So this is the convolution integral. Okay, so from this equation I can say the convolution of two signals x of t and h of t can be expressed as, now the convolution of two signals, one signal is x of t and another one is h of t. Now if I want to write the convolution of those two signals x of t and h of t, that can be expressed as y of t equal to x of t convolution. So star is a representation for convolution. This is a symbol for convolution. Okay, so y of t equal to x of t convolution h of t, or x of t star h of t. This is for convolution. Okay, simply this y of t is equal to integral minus infinity x of tau h of t minus tau d tau is nothing but the convolution integrals in convolution. So there are two signals x of t and h of t. Now the convolution of the two signals can be expressed as y of t equal to x of t convolution h of t. So for this the formula is this one. That is y of t will be equal to integral minus infinity x of tau h of t minus tau d tau. Or you can write the formula as integral minus infinity x of t minus tau into h of tau, x of t minus tau into h of tau d tau. We can write in that way also. Okay, so this is the concept of convolution. Simply the convolution of two signals x of t and h of t can be expressed as y of t equal to x of t convolution h of t, or the formula y of t will be equal to integral minus infinity x of tau h of t minus tau d tau. Okay, so this is the formula, that is x of t convolution h of t will be equal to this one. X of t convolution h of t will be equal to this one. Now simply we can write like this. So x of t convolution h of t, x of t convolution h of t will be equal to integral minus infinity plus infinity x of tau into h of t minus tau d tau, t minus tau d tau, or that can be written as integral minus infinity to infinity x of t minus tau h of tau d tau. Okay, we can use any one of these two. Okay, generally we will represent it as integral minus infinity x of tau h of t minus tau d tau. Okay, so this is simple introduction and concept of convolution. Okay, we all know that a convolution is a mathematical operation used to express the relation between input and output of an LTI system. Okay, we all know that this convolution is nothing but a mathematical operation used to express the relation between input and output of an LTI system. So how it will relate the input and output means, here the convolution relates input, output and impulse response of an LTI system. That is, it will relate the input and output with the help of impulse response of the system. Okay, now the convolution relates input, output and impulse response of an LTI system as y of t equal to x of t convolution h of t. We all know that y of t is equal to x of t convolution h of t, and x of t convolution h of t formula is integral minus infinity x of tau h of t minus tau d tau. So this is the formula for x of t. There are two signals x of t and h of t. The convolution of the two signals will be given by integral minus infinity x of tau h of t minus tau d tau. So finally I can write y of t output will be equal to integral minus infinity x of tau h of t minus tau d tau. Here the limits here, the limits in general, the limits of the integration in the convolution integral, in this convolution integral, for the integration we have the limits in general. Those limits depends on whether the signal x of t and the impulse response h of t are causal or not. That is, here the limits in this integration depends on whether the signal x of t and the impulse response h of t. So the limits will change when the change in x of t and h of t, whether they are causal or not. So some signals may be causal and some signals may be non-causal. The same way, impulse response h of t causal or non-causal, depending on that signal x of t and impulse response h of t as causal or not. We have different limits of this integration in the convolution integral. So I will give the four cases. Okay, because here x of t and h of t both are causal. One is causal, other one is non-causal. Both are non-causals and the reverse. Okay, we have four cases. For four cases we have different limits. See, y of t equal to the same for integral minus infinity x of tau h of t minus tau d tau. If both x of t and h of t are non-causal, both are non-causal. Okay, both this x of t and h of t both are non-causal. We all know the causal, non-causal, everything. I explained its concepts clearly, okay, in the previous chapters. Now y of t equal integral minus infinity x of tau h of t minus tau d tau is the equation. That is, limits are from minus infinity to plus infinity. If both x of t and h of t are non-causal, both are non-causal, the limits are minus infinity plus infinity. See, formula is same, x of tau h of t minus tau d tau, but the limit changes from minus infinity to t. That is, if x of t is non-causal and h of t is causal, here the signal is non-causal and the impulse response is causal. Impulse response of the system is causal. Okay, so as x of t is non-causal, x of t is non-causal and h of t is causal, the limit changes from minus infinity to t, minus infinity to t. Okay, and next the limit changes to 0 to infinity if x of t is causal and h of t is non-causal. X of t is causal and h of t is non-causal. H of t non-causal and x of t is causal. So the limit changes from 0 to infinity. And the last one, if both are causal, both are causal, that is x of t is causal and h of t is also causal, then the limit changes from 0 to t, 0 to t. Clear? So here simple for your reference, if h of t is causal, h of t is causal, then the upper limit is t. Here also h of t is causal, the upper limit is t. Okay, now x of t is also causal. If x of t is causal, the lower limit is 0. The lower limit is 0. So x of t is causal, the lower limit is 0, because simple, a causal signal is the one which will available only for positive t, that is for t greater than 0. For positive values only the signal is present, and for all the remaining negative values, that is negative t, there is no causal signal, there is no signal. Okay, so from minus infinity to 0 there will be no signal if the signal is a causal. If the signal is a causal, that x of t equals 0 for t less than 0. Hence for causal signal the lower limit starts from 0. So these are the simple techniques to remember the limits. Simple. So x of t is causal, then it starts from 0. X of t is causal, then it starts from 0. Okay, the same way h of t is causal, h of t is causal, it extends up to small t, and h of t is causal, the upper limit is small t. Okay, so if you remember these two, you can write all these three equations. If it is non-causal, then go for minus infinity to plus infinity. And see here, x of t is causal, that means it starts from 0, and h of t is non-causal. As it is non-causal, the upper limit is up to infinity. The upper limit is up to infinity. Okay, see here x of t is non-causal, so the lower limit is minus infinity, because non-causal it is from minus infinity, so minus infinity, and h of t is causal, so upper limit is capital T. As h of t is causal, the upper limit is capital T. Both are non-causal, that is from minus infinity to plus infinity. Both are causal, that is from 0 to t. So in this way we can easily remember the limits of the integration in the convolution integral. So you can remember the upper and lower limits of the integration in the convolution integral based on the x of t and impulse of h of t as causal or not. For different conditions we get different equations as shown here, and I explained how to remember this along with the concepts of, because you know the concept of causal and non-causals. Okay, based on those concepts we will get the limits. Okay, so this is in general about convolution and limits, convolution and limits of the integration in the convolution integral. Okay, now in this class I explained you about the introduction of convolution and the concept of convolution, and I given the formula for convolution, how the input, output and the impulse response of an LTI system are related. I have given the formulas, and in the convolution integral the limits of the integration will change, that is those will depend on the signal x of t and the impulse response h of t, whether these two are causal or not. So based on those conditions we have different limits for the integration. So I explained for all the different conditions. This is today's class. Okay, in the next class we will see the properties of convolution, and then we will go for the convolution in time domain and frequency domain. Okay, time convolution theorem. Okay, we will go for the theorems, frequency convolution theorem. Okay, thank you, one and all.